Welcome to this lecture on endocrinology, specifically focusing on the G protein-coupled receptor family. Today, we are going to explore how your cells communicate with the outside world without ever letting messengers inside. This is one of the most important systems in your entire body, controlling everything from your heartbeat to your metabolism. Let us dive in and see how it works. To understand how this works, imagine your cell is a highly secure factory. The lipid cell membrane acts like completely locked doors, keeping outsiders away. When a hormone, acting like a delivery driver, arrives with an urgent message, it cannot just walk inside. Instead, it hands the message to a security guard stationed at the membrane. This guard is the G protein-coupled receptor. It takes the signal and relays the instructions to the workers inside the cell. This brilliant system allows your cells to respond to vital outside signals while maintaining strict security over what actually enters. Now that we have our analogy, let us look at the actual biological structure. The G protein-coupled receptor is the largest and most diverse group of membrane receptors in eukaryotes. Structurally, it is a single, long polypeptide chain. This chain threads back and forth through the oily lipid membrane exactly 7 times, which is why scientists often call them 7 transmembrane receptors. The portion of the receptor that faces the outside of the cell forms a specific docking station. This is where water-soluble hormones, also known as ligands, bind to deliver their chemical messages. While the outside of the receptor waits for a hormone, the inside is already prepped for action. The inner-facing portion of the receptor is physically attached to a specialized complex called a G protein. This G protein is not just one piece. It is made up of 3 distinct subunits named alpha, beta, and gamma. You can think of this 3-part complex as the internal walkie-talkie of our security guard. It sits quietly on the inside of the cell membrane, waiting for the receptor to give it the signal to start broadcasting the message to the rest of the cell. So, what happens when a message actually arrives? When a hormone binds to the outside docking station, the entire receptor physically changes its 3-dimensional shape. This shape change twists the inner portion, which signals the attached G protein to wake up. The G protein does this by swapping out a resting molecule called GDP for a highly active molecule called GTP. Once this swap happens, the G protein breaks apart and kicks off a massive chemical chain reaction inside the cell. The message has been successfully received and amplified, all without the hormone ever crossing the membrane. Let us bring all these structural pieces together in this diagram. Notice the lipid bilayer acting as the main barrier. Embedded within it is the GPCR, clearly showing its 7 loops passing through the membrane. At the top, you can see the ligand, or hormone, docking into the receptor. Look at the bottom, inside the cell. You can see the G protein complex with its alpha, beta, and gamma subunits attached to the receptor. When the ligand binds, the alpha subunit will activate and move along the membrane to interact with the effector enzyme, shown on the right, starting the cellular response. Before we look at the mathematics of this system, we must understand why it is so crucial. Many life-saving hormones, like adrenaline, are water-soluble. They physically cannot pass through the oily cell membrane. Without GPCRs, your body would be completely deaf to these signals. Furthermore, this system provides massive signal amplification. Just one single hormone molecule binding to one receptor can activate thousands of enzymes in a fraction of a second. Because they control so many vital processes, GPCRs are the target of nearly half of all prescription drugs on the market today, including asthma inhalers. To truly understand how sensitive these receptors are, we use a mathematical model. This formula calculates the fractional occupancy, which tells us what percentage of receptors are currently bound to a hormone. The symbol Y represents this fractional occupancy, ranging from 0 to 1. The symbol L in brackets is the concentration of the free hormone floating outside the cell. Finally, Kd is the equilibrium dissociation constant, which measures how tightly the hormone binds to the receptor. If the hormone concentration increases, the fractional occupancy Y also increases. If the receptor has a high affinity, Kd is very small, meaning it takes only a tiny amount of hormone to fill the receptors. Now that we have our formula, let us apply it to a real biological scenario. Imagine a heart muscle cell responding to adrenaline. We are given a dissociation constant of 4 × 10 to the -9th molar and a matching adrenaline concentration in the blood. We want to find the percentage of occupied receptors. We start by writing our fractional occupancy formula. Next, we substitute our given values for the ligand concentration and the dissociation constant into the numerator and denominator. Because the values are identical, the math simplifies beautifully to 4/8. Our final answer is 0.5. Physically, this means exactly 50% of the receptors are occupied, triggering a moderate increase in heart rate. The example we just solved reveals a fundamental rule of endocrinology, and we can prove it algebraically right now. We want to establish what happens anytime the hormone concentration exactly equals the dissociation constant. Mathematically, we set L equal to Kd. We then take our standard binding equation and substitute Kd wherever we see L. This gives us Kd divided by Kd plus Kd. Combining the terms in the denominator gives us 2 Kd. The Kd terms cancel out perfectly, leaving us with exactly 1/2, or 0.5. This proves that whenever the hormone concentration matches the dissociation constant, exactly half of the receptors will always be bound. Let us look at a more complex example involving drug design. A scientist is designing an asthma drug with a Kd of 2 × 10 to the -7th molar. To stop an attack, the drug must occupy 90% of the receptors. We need to find the required drug concentration. This time, we are working backward. We plug in 0.90 for Y and our known Kd value. To isolate L, we multiply both sides by the denominator. Next, we distribute the 0.90 across the terms. We then subtract 0.90 L from both sides, leaving 0.10 L. Finally, dividing by 0.10 gives our final answer. The required concentration is 1.8 × 10 to the -6th molar. Let us analyze the result we just calculated to prove a crucial pharmacological lesson. We want to see how much drug is needed compared to its baseline affinity. We take our required concentration of 1.8 × 10 to the -6th and divide it by the dissociation constant of 2 × 10 to the -7th. By adjusting the decimals, we can easily see this simplifies to 18 divided by 2, which equals exactly 9. This proves that to push a cellular response from 50% to 90%, you cannot just double the dose. You must increase the drug concentration nearly tenfold, specifically 9 times the Kd value, to force those last few stubborn receptors to bind. We have covered a lot of ground today, so let us review the most important ideas. First, G protein-coupled receptors act as the ultimate cellular communication gateway, utilizing a unique 7-transmembrane structure. Second, they are essential because they allow water-soluble hormones to dictate cellular behavior without ever crossing the lipid membrane. Third, by understanding the mathematical principles of receptor binding, we can precisely calculate exactly how much hormone or drug is needed to trigger a specific biological response. You now understand why GPCRs are not just fundamental to endocrinology, but are the absolute cornerstone of modern medicine.